It's my absolute pleasure to introduce the last of our Nemmers Seminar speakers. And so I hope you agree that we've had a fantastic quarter of talks in the arena of organic geochemistry. And this one is moving literally into space. And so I'm happy with the way the order of this ended because we get to kind of culminate our wander through understanding of organic geochemistry and isotopes into now thinking about how those isotopes present themselves in the actual universe. And so it's my pleasure to introduce Elle Chimiak, who is currently a postdoc at Boulder and Caltech. She did her undergraduate at Amherst College in chemistry and English, before being a lab manager for a while at Princeton, before coming to my alma mater, Caltech, to work with John Eiler on all the fancy new math specs in the basement, as well as my former PhD advisor, Alex Sessions, where they actually got it to work. And I was a senior grad student at the point where all of these new toys were coming in and they were trying and pulling out their hair, trying to get like a measurement. And so when I left, it was like, can they make a measurement? And then I left and everything went great. And so Elle's now going to tell you about that trajectory and all the great things they were able to do once I got out of the way.
So okay, now that I've graduated, it broke. So it held it together for me. But thank you for that introduction. And yeah, so today we will be discussing prebiotic fingerprints is kind of what I call this synthesis area. And it's really going to be how, if we are in space and we manage to get a molecule to measure, how we can figure out where it came from. And that's the fingerprints. You can think of yourself like a detective. And as I said, there will be chemistry, but we will keep it simple. We will go slow. And if you don't understand the chemistry, please feel free to raise your hand. I would much rather explain things than not. So, I like simple problems. One of these very simple problems is how life started. And there are kind of two general flavors of people looking into this. One would be the top-down folks, and that is, we're alive, I hope. So we can go backwards in time. And the other people are, I call them the Lego builders. If we didn't have life, we just had a bunch of Legos, how do we make that life form? So going kind of first group, you have people looking for Luca, the last universal common ancestor. So you can make your fancy trees of life and try to find the first one. You can also look at the limits of life, and this helps people like me, because if we can constrain space, so your temperatures, your pHs, where we can have life, then we can start to think of environments where we could have made life. And finally, of course, our beautiful astrobiologists who are now trying to find other planets that might have life. And again, this just expands our phase space diagram, because typically when we're considering where life formed or where life could form, we want to actually have it in a place where life would then survive the second it is formed instead of immediately dying. So then we go into kind of the my people. And those are the bottom up. I like small things. And this would be people looking either, say, for environments. So modeling the early Archean, not easy to do. But if we can understand what environments are there at that time, we can understand what we had access to on Earth to make life, or looking at other planets as well. Then the next one, very much my people, are the synthetic people. And so those are the ones saying, if I'm in space, what syntheses are happening? And you can do this through a variety of measurements, such as the new fancy telescope, the James Webb Space Telescope, that does not have a better name, that is currently out there surveying for different molecules. And there are also lab components to this where people are actually shooting lasers at these molecules on ices at like 40K to see what forms. And finally, the kind of next group of people past what I do, they take these molecules and try to say, make proteins or make micelles, or even just make the amino acids combine with each other without life. So this is always without life. And we're going to kind of be focusing on that middle one, the Goldilocks, as I like to call it. And overall, we're going to first talk about how the components of life could form. So all the theories out there, or some of them, the past measurements that have been made on meteorites. And then we're going to go into kind of the juicy stuff of the talk, and that's the site-specific work. We will really go into how the orbit trap works, and hopefully will inspire some of you maybe to want to do measurements on it. and then go into actually the measurements I made and what they told us about synthesis. Finally, if we have time, we will actually discuss how I then use those measurements to try and quantitatively come up with the different pathways that could be forming organics. And so if we go with chemical approaches, we start simplest with atoms. We make atoms with stars through nucleosynthesis. So a star explodes, reactions are going on inside, and then these beautiful atoms are released. So chunks is kind of what we need for life usually. And those can combine in a variety of environments from the interstellar medium. I will say that word a lot, so just an FYI. Solar system is here. I go past the solar system. There is dust everywhere. And in that area, chemistry still happens. And you have some hot areas, but the area we're super interested in is the cold interstellar medium, 10 to 40 Kelvin, super cold. You can also have these simple organics forming on meteorite parent bodies, so asteroids or potentially comets, or just bodies that got large enough but still did not overheat. And finally, actually on lake environments around early Earth or other planets. These then, in those environments, can combine to make larger organics, say amino acids, which I love, or lipids or sugars, all of these compounds that you need for life. And I should state the ones up there are ones that actually can form abiotically. So, and finally, you can take those together again and make structures. And so chemists are working on all of this. We will be focusing on today is the stuff I work on, and that is these larger organics, and specifically alanine. And why alanine? A couple of reasons. One, all known life has it, so it seems that life uses it. Two, it is chiral, so everything in life has a handedness. If you put it in a mirror, it would look like each other, but you can't overlap it. Amino acids and proteins in life are typically L-handedness, much like my name. The best handedness, although there are some crazy ones that are not. But it is the simplest of these. So if you want to study a very useful for molecule, a chiral one, alanine is a great way to go. And also there are multiple theories that predict that alanine might have been one of the first amino acids that could have been used in life. And so again, go team alanine. And finally, this also was part of our decision making. If you take a abundance in meteorites, as we will see in a couple slides, alanine is one of the most common or most abundant. This still means you get 10 nanomoles per gram. So you need to go with the most abundant, especially if you have a new method. What we'll hope to answer by the end of this talk is what precursors did we need to make alanine? Precursors here just being the reactants. So what simpler molecules do we need? What are the physiochemical boundary conditions for the synthesis that makes alanine on meteorites? So physiochemical, big word, just physical and chemical, temperature, pressure, amount of water, whatever. And finally, what places could be satisfied by these conditions? So both past and present. So places wise, these are the biggies that I will be talking about. I know it does not encompass many places at all. Early Earth, early Mars, even maybe present Mars in the subsurface, but I doubt it. Enceladus, I have doubts.
Yeah, words.
Shots fired.
Yeah. I'll go there.
I'll be over here sharpening my knife.
If we can find it, I will be very happy, but I'm a natural pessimist.
Me too.
Yeah, if you look at early meteorite literature, all of the early detections of organics are contaminants. So we go very pessimistically. Enceladus, other parent bodies, and this would be much more for the organic chemistry side, not the life side. And then other solar systems, which I very much hope could have life. Hope being my strong word in this. So why do we use meteorites at all? Why don't we go into life? Why don't we go under Earth? Earth has all these compounds. If I'm looking for amino acids, I can go into a lake, I can take a sample, I'll find amino acids. Well, first of all, meteorites have a large diversity of compounds. So, it's good to go there instead of, say, a dead, overheated asteroid that has none of them because it overheated. But also, meteorites don't have life. If I go into that lake bed, almost all my amino acids are contaminant for what I want, not for what Maggie wants, but almost everything I would measure would be produced by life. So how am I going to figure out how we make these without life? And that is go to a meteorite. It had this, same kind of components that we got to accrete in the solar system, but never had this, pesky little issue called life. So in alanine formation. And in most prebiotic organics, we would consider a couple different pathways of formation. And one is in the interstellar medium, and that is going to, for all intents and purposes here, include the outer solar, pre-solar nebula, which is also super cold and not well shielded, but we're just going to call it the ISM because otherwise it's a lot of words. The next environment is I can be in the solar system, but I can have precursors that came in with the interstellar medium. So when I form my solar system, this big, cloud of dust that collapses, so you do get to bring everything that was in that cloud with you. And this includes, as we know from measurements of the interstellar medium, things like aldehydes. Like acetaldehyde has been detected, or cyanide, tons of cyanide, which is just what you want for life. And finally, the solar system itself, without anything exogenously brought in, just solar system. So in the interstellar medium, we actually already know that ion molecule reactions on grains in the lab can form organics. We know this has happened. We've taken methanol and cyanide on ice, which is extremely hard when you're at 10 to 40 Kelvin. You zap it with a laser, and out you get amino acids, amines, and nitriles, which is a little obvious because you have cyanide. You also, in the early solar system, you're making your beautiful, beautiful asteroids and parent bodies for your meteorites. And you have things like acetaldehyde again and other aldehydes. You have cyanide, you have ammonia, all of these again detected in the interstellar medium. And you have ice, very useful because and in addition to that, some radioactive nuclides, which are going to, of course, decompose, heat your meteorite parent body, and that gives you water, and you can actually potentially have some nice little hydrothermal systems going. Great for chemistry. And that again, you get amino acids, amines, hydroxy acids. You actually also get, which I didn't mention on the other slide, you get some purines, you actually get some of the components for DNA that have been detected on meteorites and produced there. And finally, I could say, I don't have anything saved from the ISM. It's all gone. So my gas cloud is mostly gone. What can I do now? And you can still do some chemistry because chemistry can always happen. I think. And some of these, the biggie would be Fischer-Tropsch type synthesis. And this is actually the reasons the Nazis got to stay in World War II so long is they figured out things like this for fuel making. You can take carbon monoxide and link it to a catalytic site. Meteorites, in fact, have all of the precious metals like platinum or very catalytic metals on them in much higher abundance than we have on the Earth's crust that we can access easily. And these can react with hydrogen. You can form long chain alkanes, and then you go through something that it's not pictured there called the Haber-Bosch process, where you can add nitrogen onto these hydrocarbons. So what will we do to constrain this chemistry? Because I just laid out a bunch of chemistry. We're going to use isotopes. Isotopes are beautiful. We all love them. Carbon here, we're going to use stable isotopes, I should say specifically. Carbon here will come in two flavors. Your protons kind of tell you what atom you have. Your electron numbers kind of tell you what kind of chemistry we're going to be doing. And your neutron numbers tell you which isotope you have. And here we have 12 and 13. This is all we will be talking about today. There are many other isotopes we could consider, but when we are setting up the instrument, you go with the most abundant, and that is carbon. 1% on Earth about is going to be your 13. So the reason we can use isotopes is because the heavier substitutions, when bonded to something else, have a lower 0 point energy. And so especially in ISM chemistry, where I'm commonly creating C+ is a very common species. If I'm trying to react out, your C12 obviously can go more quickly, just because you have less of a well. And although I'm making this well look very large in this figure, it is extremely small, those differences. The other thing is this lower 13C at a lower 0 point energy adds stability. And once we are in our 40 Kelvin system here, we have this beautiful reaction going on. This most common carbon reaction in the ISM. Carbon monoxide, C+ with that C+. So the red here is heavy carbon 13C, the blue being 12C. It goes back and forth. And if we were in a normal above 10 Kelvin system, this really would go back and forth. But in the ISM, where I'm at 10 to 40 Kelvin, the way out is 35 Kelvin, which means my ambient temperature, I go through, I'm really happy. I'm like, oh, exothermic reaction, this is great. Let's equilibrate. And you do not have the energy to go out. So you're just stuck. And because the oxygen is one of the more abundant species in the ISM, this is a very typical reaction that goes, and this sequesters most of your 13C into the what we call CO pool. And CO pool means carbon monoxide and anything that comes from carbon monoxide. This also means that everything coming from that C plus pool is going to mostly be 13C deplete. And the amounts of enrichments and measurements are hundreds of per mil enriched in the ISM for that CO pool. I would love to give a precise number, but the measurement error bars on a lot of these are about 200 per mil. Still, even so, if I'm 400 plus or minus 200, it's still very enriched relative to terrestrial, which, as you can see in this diagram, is kind of on that 0 and below. And just for people who need, there's just a little notation explanation in that bottom corner, the bottom left corner. Chemical isotope effects are going to range on the kind of the order of 5 to 30 per mol. So still far less than that inherited, or if it is inherited, CO isotope anomaly, hence it being fingerprinting mostly. So in the ISM source, kind of the theory would be, we have this light pool, so you make your methyl groups from that, and you have your heavy carbon pool from CO. If you're in the protosolar nebula, you are mostly light carbon. I think Lyons et al. 2018 gives an estimate of negative 48 per mil. So very different, hundreds of per mil enriched versus negative. And if I make my alanine or any other molecule from that, my carbonyl sites are going to be very enriched again. They should inherit this super heavy signature. Even if it's only partial inheritance, it's still going to be really heavy again compared to that light pool. So I made in the solar system, on the other hand, my isotopic intramolecular differences. So site 1 to site 2 are going to be much smaller. So if I go back to these theories that I laid out, the Jamie Elzilla very nicely did a set of experiments for this first mechanism, and she found that your heavy isotope actually ends up on the methyl site. This is the craziness of zapping things with radiation, is you can get site mixing in these, and this would actually map out onto our site specifics with, so just to orient people, C1, C2, C3, this is alanine. So I don't assume that everybody automatically knows isotope notation, which is fine. Oh, good, I have my pointer. So this would give us 2 light sites and a very heavy C3 site. And again, that high on this could be like 1 to 200 per mil. So very high, which again, if you are making new methods, is great. The next one that we'll look on is a parent body reaction using, again, our precursors. So we have acetaldehyde, which is that red and blue molecule. And we also have cyanide. I put cyanide here as 13C poor. I will just give the caveat that that's heavily debated within the community. But this would give you a low pattern for Strecker synthesis, which we can see here. Okay, low, high, low. So you see again, C1 is low, C3 is low, because those are both coming from this 13C poor pool, and C2 is extremely enriched. And the C2 enrichment is truly going to be the signature. Again, cyanide is a debated compound. And finally, formose chemistry. So in formose chemistry, you take formaldehyde and you react it with formaldehyde. And so your isotope structure is a little bit more boring. It is, everything is very enriched. Everything is just 13C heavy. And the other opposite end of that would be the Fischer-Tropsch, where we're taking everything from this lower 13C, CO gas, and reacting it with each other. Now everything's super low, as you see in that purple. So these are actually our predictions. And going into this experiment, these were my predictions. I said, okay, I have these different scenarios. I actually had about 8, but let's stay simple. Here are my 4. Can we distinguish a pattern that will tell us? So this gets us to measurements. And so just quick overview. Our chemical approach, we're going to be investigating the syntheses that create small organics such as alanine. In meteorite amino acids, we're going to use those because they're diverse and have no life. And alanine in this have a variety of reactions that we discussed. The 10 to 40 K temperatures are going to give us these high 13C enrichments. And we went through predictions, but each reaction has its own, yes.
Okay, sorry,
Yes.
I don't want to get lost.
Go ahead, please.
Okay, I have 2
Thank you.
questions. I've been getting really held up on why 10 to 40 K is like ideal.
It's not ideal. It's just typical.
It's so cold.
No.
It does so cold.
It is.
How
Ice
can
has I think
chemistry
the
like-
hardness of granite at that. I
Yeah.
think at that.
How can like chemistry even like happen? The kinetics. Like,
That, yeah. So okay. So it is. Love that. question. It is fascinating. Jeff Blake does a lot of work on this, and it's much more of a thermodynamic range at that point. And it is because you have, so I'm just going to go back a tiny bit to this slide. Here we go. That C plus is so reactive.
Right.
Basically,
okay.
you ionize the carbon. It's a plasma, right? Ionized molecules will react. And what is happening is they're going onto these grains, these ice grains and dust grains. And there it's a local environment. It is very cold, but if you have two molecules that are close to each other and they can react at all, and it's exothermic, they can.
Okay.
It is very low reaction rates, but you have zillions of years.
The statistics of that are, okay.
Yeah.
Okay.
No, that is correct. It is.
Okay.
We do not want that because of ideal. We just want it because that's
The typical, the most
Yeah.
average. Okay, my second question is actually related to that.
Oh, cool.
I actually don't understand why, or like what the relevance of like site specific, like what are we gleaning when we're like. oh,
We're gonna
it's
get to that in the
okay.
next section, but good. I love it.
Okay.
That you just set me up. So first we're gonna go into why we didn't do site specific, and then I'll tell you why we need it. So we have this information on site specific, and why didn't we do this all along, right? It seems great. We can tell so much. It turns out that most mass spectrometers don't have the resolution to really get beyond n and n+1, which is already, I should state, so useful. But I'll say take a compound like this derivatized alanine, stick it through a GC, separate out my alanine, and now that n+1 peak combines all my carbon, hydrogen, oxygen, and nitrogen +1 peaks. So my deuterium, my 13C, my 15N, all of these +1 peaks are melded together. And especially when you have a meteorite organic, where everything is extremely enriched, this melting together is even worse for you. So, I mean, I was always even just fascinated that we could measure this at all, because how do we just get a carbon-13 measurement is first I derivatize my alanine because it is not very volatile. Then I combust it, so I separate it out and I combust it and oxidize it. So I'm going to make something like CO2, let's say, and then a bunch of gases that are not CO2 or have any carbon, and we just get rid of those gases. That is actually how we deal with the n+1 problems. We say, yeah, I don't want any of the nitrogen or hydrogen, just get rid of it. And then I measure 13CO and 12CO. And this, again, all of the site-specific data is now scrambled because all of that CO is measured together. And so the pros is we had things like delta 13C values for the molecular average, which has been super useful. The cons is that all of that structural information is lost. What have we been able to tell with that? And I should state there's like 40 now years of literature on this. I am getting old. But this is in 2012, like getting molecular average measurements on more than one meteorite was already a huge feat and changed how we view this. But even then, you can see one, especially when you're doing meteorites, meteorite to meteorite. So the circles here are this Pissarello et al. Paper from 2004. She recently passed away, but was one of the big heavy hitters in the community. And then the squares are Jamie Alzilla's paper, and this is all just on Murchison. You can see that there's actually a lot of scatter because sample to sample, your bulk, so your molecular average isotope ratios are actually quite different. And two, what I can say from this, so on the left is amino acids. The bottom, that's number of carbons. So C2 would be carbon, number of carbons. So C2 is glycine, C3 is alanine. It just is adding a carbon on. You can see that there's kind of a trend, especially if you get rid of, say, if this doesn't exist, there's a much more compelling trend that we must include all data, that you overall decrease in delta 13C with your chain length. And this is for hydroxy acids and amino acids. So molecular average wise, right, we go from these heavy kind of red colors to these lighter blue colors, but we can again only tell full molecule. I don't know what site's doing that. And this is the issue, is to get this pattern, you can have just the 13C enrichment on the carboxyl group alone. This could be one type of synthesis. You could have it on the amine bound carbon, so on that C2 site. This could point to, say, Strecker synthesis, or you could have it on both sites. All of these point to, well, one could be different syntheses. You could also have this, say, just if you're fractionate, if you have a step that adding each carbon fractionates it, like Foremost might do that. So you can't really get to the chemistry question completely. And two, kind of like one of the side things is cyanide is not well constrained for isotope value, and so being able to actually constrain it. Nitriles are extremely useful in prebiotic synthesis, being able to know, say, did it come from the ISM or not. is a big utility for us. The other thing that we note is that if I add a methyl, so that C2 site, that pink site in the middle, if I add a CH3 instead of an H, for no understandable reason, your isotopes become heavier. By no understandable reason, I mean them synthetically. So we don't know if that's, am I completely doing a different synthesis? Could be. Or is that site just from a really heavy carbon pool? And so we want sites, so we actually have been able to say, given that you are averaging across all molecules, by getting hundreds of compound measurements, we can say something. What I'm hoping to show you with this is that by getting a single alanine method measurement, we can actually say quite a bit with that one measurement. And so the hope is to add on to it. So it's not a replacement. It's a parallel. And so yes, our past measurements, they are resolution limited. Those instruments though are a lot cheaper. So it is actually really useful, and most people know how to use them, and they're set up for most people. They relied mostly on combustion, for carbon to be to CN2, but you can also do nitrogen measurements for molecular averages. And in the past, findings have been like that you have this overall decrease in delta 13C of the molecular average with an increasing carbon number. Again, we don't know what site that is. And that if we have a methyl group on the amino or the hydroxy acids, then we have at that same carbon number, we have a heavier molecule. So what we're going to do is we're going to use the Orbitrap, which is a fancy new machine that I got to spend like 3 years building. We're not building, but I'm making work and getting very used to tiny GC parts with. And so the Orbitrap basically get volatile compounds, or you make your compounds volatile. And this can be a huge mixture of amino, carboxylic acids, et cetera, that you would get from a meteorite. You separate them out, and we'll go through that step. And then you measure it on the Orbitrap, we'll also go through that step. So we derivatize into, in this case, the trifluoryl methyl ester. And that again is just to make it go through the GC. Then it goes through the GC, and anybody who's used a GC column here just knows that just separates out all my compounds. But I don't want all of these compounds. I want one compound, and that is alanine. And so we actually built this front end, which has a sample reservoir. And so what I can do is I can select the alanine peak, and instead of routing it to my GC, I'll just route it into this reservoir that will allow that time that it has to go for, say, an hour. And this just allows me to get more measurement data. Because of how the Orbitrap works, effectively you're cutting out, if you just go straight through, you're cutting out most of your peak data. And so what that looks like, so this is actually one of the chromatograms from the paper, and for Murchison, is you see when it just becomes this huge blur here. This is alanine. This is actually alanine for Murchison. This is just peaks that came out before it. This is about NL of like 185. Any ions more than that, and the instrument doesn't even put them into the Orbitrap, and so you do want to spread out your peaks as much as you can. And so what that would look like for a typical measurement is I start at the left, and I'm sending everything to the mass spec so that I can see what's coming out. And I have a marker peak, here it is starred. And I know that X number of seconds after that marker peak at this time, so everything's automated now, but I actually have to manually turn a bunch of knobs to make everything go into the reservoir. And then once that peak elutes, you put helium. So it's just helium after that going in with your peak. And so then it goes into the Orbitrap. What is happening there? So I take this derivative again and I ionize it. And that ionizing is actually one of the key things we need for this. Because if I just ionize this and measured it, I get exactly what I got before. I get a molecular average. It'd be great, but not really what we're going for is reinventing the wheel here. Instead, you cut it. So you can see here, I am now losing my C1 site. So these are color coded as before, C1, let's see, C1, C2, C3. And so let's go with this guy. Here we go. So I cut off my C1 site here, or I can cut off my C3 site here. These are the two fragments I used in the paper. There's like 100 fragments that we could have used. These were the two kind of best candidates because they're the best signals. So I ionize it, then I go through a quadrupole, which is kind of the lower end mass spec in this instrument, because you don't want all of the ions to go into your source. Here, we just wanted our 140 fragment in this example, and so I'm going to take everything else away. This just decreases all of the noise that you can get in your signal. And then we go, so there's like a C-trap step, that's just ion purgatory while I get enough ions to inject it then into the Orbitrap. the Orbitrap works because everything is an ion. I'm going to go back and forth in this little football, and my speed is contingent on my mass. And it goes down to resolutions where I can distinguish a 13C substitution, so that would be at either site, I should say, a deuterium substitution, a 15N substitution, etc. These resolutions get up to 500,000 full peak half max. But because they are packs of ion, one of the reasons I want to select out to make it just what I want to measure is ions interact with ions. And so it is a bit of a game. But here are actual spectra that I took. These are, again, of the emergency meteorite itself. And you see this is my beautiful 140 peak. This is unsubstituted fragment. And this is my 15N peak fully resolved. And this little peak here is actually my deuterium peak, which I'm currently getting measurements on. And then the 184 peak, you can again see it is fully resolved from its other peaks. And that is kind of the power of the Orbitrap. Is now this amount of resolution, there is no orbit. So it is really useful for us. So what we're going to do is we're going to just do some basic linear algebra. And I like the alanine because it's just a 3-carbon problem. The other, we use the same derivatizing agent, so we can actually back out those numbers. But you get your C1, C2, C3 measurements. So NASA actually did this one for us. Thank you. Then we have our C1 and C2 fragment and our C2 and C3 fragment. And you can just, again, do linear algebra and back out C1, C2, and C3 separately. So the exact methodology is we had 2.6 grams of this meteorite from the Smithsonian. We put it, or we didn't, Jamie, who was very good at this, put it in a glass ampoule with water, centrifuged it, and you take the supernatant, you isolate it, and you actually hit it with HCl for 24 hours. And that step terrified me, I should say. And I was like, there's going to be chemistry, we're going to degrade everything. And there have actually been there are papers on this. I think Zita Martin, I believe her 2009 goes over this, but there have been papers where they've compared just with water and then with HCl. And if you do everything else downstream, right, you derivatize and you run it, your isotope ratios stay the same. The only thing that changes is abundance. And so I think it might be that you're getting some absorption onto the glass. You also don't want. So just an FYI, that step is scary too though. And then you do what we call desalting. So if I have a bunch of chlorides, also my meteorite has some amount of salt on it. We don't want any of that, especially iron. And so you desalt it, you use a Dow-X column in this case, evaporate it, and then Jamie at NASA kept 85%, and I got a whopping 4.4 nanomoles to do chemistry on, which is terrifying when you have to derivatize it. But we did, and she got so much data. She got all the amino acid concentrations, the racemic, so D to L, the molecular averages, and I got just these 2 little pieces of data which were site-specific. And probably took more time than she did. But this is what we found, and this is exciting. So I'm going to walk you through this graph, and just a reminder, in the lower right-hand corner, I will always have alanine, and it's labeled with its sites, C1, C2, and C3. Organic chemists would just use those numbers, and apparently I should not always do that. So what we can see is C1 and C3 are kind of more of our solar system expected values. They're in that -30 per mil range. Our C2 is super enriched, and the lowest value that I could find for an ISM sourced CO within 1 standard error was about 119 per mil. Granted, again, this is the tail of that error bar. It's like, again, 400 plus or minus something. But the C2 site likely does have some inheritance from the interstellar medium or cold outer solar system. And this clearly matches exactly one prediction that we had made, which is structure synthesis. So that's also great. Because that does let us it was hypothesized from the molecular average data that it was likely structure synthesis that would cause these isotope anomalies on the molecular average level. This was actually our way of being able to prove it, or prove it better, because you can't fully prove it. So what we can see is that the Orbitrap can resolve these species, and I should actually state, on tiny samples, you can't get 1 per mil, but you can quite regularly get 1 per mil and below when you have more than 4 nanomoles to work with. And we can actually now go down to about 10 femtomoles of a sample per measurement. So you can get really small samples, and that is also where this instrument just blows those things out of the water. And you can separate and trap your peaks, so it does not need to be a pure mixture. And on the meteorite, we actually found the values of -29, positive 142 and negative 36. The error bars on these are around almost 20 per mil. And that is because the 184 peak is far less abundant than the 140 peak. The 140 peak measurement in this paper has about a 1.5 per mil measurement and used less than a nanomole sample. And then the synthesis to produce alanine, we think that the measurements are through Strecker synthesis. In the paper, I know I go into this side hypothesis, which I'm happy to discuss, which is pyruvate reductive amination. But let's just stick on Strecker synthesis for ease of discussion. And so we have this amino acid, alanine, which is in the far right-hand corner. All of these steps are the steps of Strecker synthesis as hypothesized. So you take a 13C rich pool with your CO, that's up here. Boop. That is pointed at me. 13C rich pool, and your 13C per pool, and that'll just make all of your side groups. So all of these alkyl chains, CH3s and CH2s should be in that kind of lower negative 36 per mil range. And then you react it with ammonia, and I should state, you cannot use ammonia. So Strecker synthesis is very pH dependent. If you do not have ammonia, you do not do the synthesis, but you make something called an imine, which is the same thing, but now with an NH. React it with cyanide, and then you make an alpha amino nitrile. So that's just, I've added my nitrile, and then I hydrolyze it, and we get this beautiful alanine structure. So if I actually want to backtrack out that entire schematic and get original predictions, which I do, I need isotope effects. And this is where actually when I joined John Eiler's lab, and he said, you do chemistry. There's this really simple chemistry. It just involves everything that'll kill you. But if you ever want your own hood, work with cyanide. No one invades your space. And so in an aqueous solution, and I varied temperature, so I have data across temperatures from 0 to 50 C. For 4 hours, we equilibrated CN, acetaldehyde, and ammonia in water, and this was just milky water. The NH3 though does drop your pH down to around pH of, I think, 8.5. And then after 4 hours, you put the terrifying step with cyanide. You actually have to add 6 normal HCl. And for anyone who knows chemistry, if I take CN minus and HCl, I just make HCN. But we did these very safely in closed systems, and this makes your alpha aminopropyl nitrile. Do not worry about that, because then it becomes alanine, basically. And that's, and what I was able to do, and it is one thing that ground truth the Orbitrap, is I actually used ninhydrin. So if you see a detected strain, they're spraying and they like see a fingerprint, that's ninhydrin. It's that purple thing that reacts with amino acids. And that can let you cleave off the C1. So we have some Strecker synthesis independent measurements, and that is how I know the Orbitrap is giving me the correct measurements when I make them. We got quite a bit of data. So we got molecular average data with an elemental analyzer, because we're making pure alanine. And we got the measurement of the C1 site. So again, alanine is down here, so C1 site, and then the C2, C3 site is in the squares here. And the dotted line, this purple line is the initial NaCN, and the dotted line up here is your initial acetaldehyde. And so we can see there's a kinetic isotope effect on your C1 site, the purple triangles. The I should state, non-shaded in ones are just much higher temperature. So those ones were hydrolyzed at about 120 C. And the squares, we have an equilibrium isotope effect at the C2 plus C3. And so what we can do is we're going to fill in values for a kinetic isotope effect in our equilibrium and backtrack. And so our kinetic isotope effect is about negative 22 per mil, which I should have mentioned on the other slide. That is actually just gotten as the average kinetic isotope effect that I see. I can tell you from the other paper, it's about a 15 per mil KIE on step 2 and a 15 per mil KIE on step 1. There are side reactions though that will occur, and I believe they would likely occur also on a meteorite. So you get about negative 23 per mil, and I mean, you can effectively just subtract it out. I actually went old school and used ratios to backtrack it and reconvert, but it gets you to about a negative 7 per mil measurement on your cyanide. And amazingly, there's exactly one cyanide measurement in the literature, and it agrees with our cyanide prediction. So that was already very exciting for us. Then we take the C2 and C3 site. This is my initial acetaldehyde, but it actually partitions. This is my alpha APN, which is 10 per mil, or yeah, 10 per mil overall, lower than my initial. But because here's the reaction, this is acetaldehyde, here's the molecule I am making. Because this molecule you can see this green carbon is really just along for the ride. He's doing nothing. We are going to assert that he is doing nothing isotopically also overall. And so this negative 10 per mil on both of those two sites averaged is probably a negative 20 per mil site that's diluted. And that's what we're going to assume. Again, that is an assumption. So we're going to assume an equilibrium isotope effect of negative 20 per mil on this middle carbon. And so it goes up from 142 to 162. And those just go back to your mean and your initial pools. And so we're going to assume that our initial 13 CO pool that we're using is 162 per mil, which is again within error of the ISM measurement, so that's good. And that our initial C pore pool is negative 36 per mil, and those will react forward. And the acid aldehyde agrees, so there were two measurements actually that came out of the same lab that disagreed with each other. They think that there were some extraction fractionations potentially, but it at least agrees perfectly with one of the two measurements. And so that to us again was heartening. So we said, well, let's, we have these numbers. Let's do what everybody refuses to do and predict quantitatively what we're going to make. And so here I'm just taking my 162 and my negative 36, and this negative 36 is going to make all of the additional carbons. So I have one really heavy side, everything else is negative 36. These are my linear aldehydes, and they match up, I would say, pretty gosh darn well, barring formaldehyde. Except for him, they match up quite well. The circles that are mostly covered are actually my predictions. So up to C6 chain length, we can predict those. So I said, okay, let's use these fake aldehydes that we've decided upon and make things. And so the first thing we're doing is reductive amination. That is just where I take this beautiful double bond to an L and I reduce it to an NH2. You can do this on many substrates, including things like green rust. So an Fe to Fe3 mixed with OH can actually do reductive amination, as Larry Barge has demonstrated beautifully. She has not measured the isotope effects, so I had to do some literature mining, and there are isotope effects due to the fact that this is a common route to make meth. Yeah, and so people actually in the DEA want to be able to fingerprint where that is coming from. And so that was great because it gave me an isotope effect of 0. So effectively, it just follows the aldehydes, but this is using data from Jose Aponte's work, and you can see with the linear, so not the branch as much, but the linear means beautifully predicts those. Then I said, well, let's take monocarboxylic acids, which we won't really get into, but any meteorite geochemist is the worst thing you can measure. They're hard to explain. The data is very scattered, but let's just try it. And there are multiple, even for the process of turning this CH into a COH, the same lab has found 2 different isotope effects, one being nothing and one being negative 19. So a normal isotope effect of 19 per mil. So we just checked both. So that's what this line is showing. Negative 19 is the bottom of that arrow, and the top is if that 0 is actually correct. And so again, these smaller C2 length we can't predict. I have other work that actually suggests that a chunk of it might be contaminant, but c'est la vie. Everything else, we're following the right trend. We're actually predicting commonly with an error. So then we said, let's take amino acids, because we love amino acids. And because then I get to cite myself, because I measured these isotope effects myself, and I feel very confident in them. So again, we're really just adding on our groups here to our measurement. And so you'll see like glycine has, doesn't quite match up, but everything else, it's again the same general trend. This 5 is actually within 2 standard errors, and so the 4. So we can at least start to predict, and these give us site-specific predictions. So if I go back and I measure a 5-carbon chain amino acid, I can fully predict what that will be sites by site, and then I can go back and say, was I right or wrong? And then we're going to take these alpha methyl amino acids. So that's where I now have 2 R groups. These likely come from ketones, or are hypothesized, if by structure, to come from ketones. And they, again, are more enriched than your alpha H's, where this is a hydrogen. And we don't know why, but I'm just going to predict that it's a negative 36 per mil because I need to go in agnostically. And if I just take the ketone measurements that have been done, I actually can reproduce them. I can predict those ketone measurements. What I cannot do is predict the alpha methyl amino acid enrichments. And so John and I had this idea that came from a paper by Petrucci et al. In 2018, where he shows that decarboxylating an alpha methyl amino acid the product formed by that is about the same stability as your alpha amino acid. And so there's a chance you can exchange with carbonate. And if you do that, you can actually predict your values. And so we were putting this forth as a hypothesis that I'm hoping to get experimental evidence to back up. The other hypothesis that I'm working on in a current paper is that you actually might have just a heavy carbon after you form your amino acids. That all deals with chemical kinetics. We will not get into that here. So somewhat of a summary here. From this one alanine measurement, and albeit a ton of past literature with molecular average measurements, we've been able to take one alanine measurement and predict an entire reaction network. We're taking a 13C rich CO pool, a 13C poor C plus pool, making aldehydes and reacting those aldehydes, and I'm saying chromium trioxide, but it's actually a metal oxide. This is just what the paper used that I stole things from, to make carboxylic acids, where you can react to make amines that can be reduced into an amine or it can become an amino acid. And this is just the figure from the paper, but I've actually predicted more since using the same data set. And you can see again, the aldehydes agree beautifully. The amines, it's usually like if you take off that first data point that uses formaldehyde, you're safe. And so what can we learn from this? Because making a pretty graph is not what we want to learn. What precursors are required? If we're using Strecker synthesis, aldehydes, cyanides, ammonium hydroxide, and water is important. That means that we cannot be pure gas phase. That also means that we are not during aqueous alteration. It needs to be warm enough. Those are our conditions. Aqueous, above freezing, and the more basic you are, the more amino acids you make. So the true thing is you can absolutely not be below pH 5. That is a hard boundary of now. But preferably around 9. Can we apply these findings to finding life elsewhere, to finding organics elsewhere? I tend to put them together because if you make a biorelevant compound, you are more likely to be able to make things from said biorelevant compounds, right? If I'm going to be life, I would much rather be in an area full of stuff I can eat or full of stuff I can make my proteins from. And so early Earth, you should have inherited some of these. Again, we have water. Hopefully there are areas above pH 5. So hopefully you can actually make some of these components and get some chemistry going. Early Mars, I would say yes. I will argue deep subsurface currently we can do some of this, but I dislike being contentious. However, I'm hoping we can find some beautiful amino acids. Enceladus, that's somewhat debatable due to the fact that if you can find pockets where you can isolate chemistry, then I'm all for Enceladus. And that's only because chemically, if you're alanine and you're in an entire ocean, you're going to break apart. Just that's life. Other parent bodies, oh heck yeah. Other parent bodies, CI chondrites, CM chondrites. These are different parent bodies. These all are a chunk of them we've even found amino acids on, but they are aqueously altered. So you did have water. You do have ammonia. You should have been basic for some period of time. So that can happen in other solar systems. And the exciting thing about that is the components we have, again, according to my theories, potentially came from the interstellar medium from whence we collapsed. Other things also collapse and form solar systems from the interstellar medium, which means that they also have these components. Potentially, I would hope that they form some amount of rocky bodies. So hopefully they could do this chemistry too, which means that in not just this solar system, you can make amino acids, you can make amines, you can make all of these compounds that you then could potentially, wait a couple billion years or wait a billion years or two and make life from. And so in conclusion, alanine, we think, based on these site-specific predictions or site-specific measurements, we were able to say likely Strecker synthesis. We were able to leverage this with the past measurement to do that. And that was by using the Orbitrap. Just honestly, a big part of it is its high mass resolution. When you have resolutions that are between 120 to 500,000, you can just resolve things really well, which allows us to say a lot more about molecules. Something I would love to discuss with people, but can't get into in this talk, is measurements I'm doing right now, which is we can actually get clumped species. So 13C2 is in that data set, pops right now. But again, we're doing like validation because standards are expensive. And I was able to use the Orbitrap to measure a 4.4 nanomolar sample. I should state the C1 or the C2, C3 sites of the 140 fragment with the 1.5 mil error bars, I could have done on like 0.5 nanomoles easily. So it's very highly sensitive. And again, Strecker synthesis would give us above freezing in basic conditions, and we then use this to model organic synthesis. This is just using the molecular average measurements. And so what I will say is, and something the Island Lab is doing now, we just want to get more compounds. And I would love for people to disprove and refine. That is actually my dream, is have a ton of people doing these measurements on this and on, say, biological compounds. We can then have the Strecker measurements and biological measurement and compare them and get biomarkers that way. And so with that very, calm presentation, I will leave you with questions.